Organic Synthesis, OCR Chemistry A 6.2.5 Part A. Using Chemistry Explained needs your active participation. You need to write notes and complete the tasks, either with pen on paper or on a tablet. Control the pace of the lesson by pausing or replaying the slides. Most important, when prompted, pause the lesson, complete the task, thinking the problem through, which means taking your time. When you're ready, continue the lesson, correcting your work. We'll start with a review of some practical skills, go on through the calculation of percentage yield, and then move on to synthesis pathways. So let's start with a look at some basic methods for organic preparations. Firstly, to increase the yield of most organic preparations, there are some exceptions which you need to be aware of, particular examples. Reactants are heated under reflux. So we have here an arrangement for heating a reaction mixture. I'd like you to pause and complete the diagram to show the arrangement that would meet the requirement heated under reflux. Pause and come back when you are ready. Okay, so here's my version. We've got a vertical or upright condenser. What apparatus would be used and why for heating the reaction mixture? Speak out your answer as if you're replying to my question. Okay, so a heating mantle would be the favorite because it reduces the risk of fire. Most organics are flammable. Now, in your school, you may just have used a Bunsen over a gauze. But preferably you would use an electric heating mantle to reduce the risk of fire. Second question, what are these dotties, these little particles, meant to represent in the diagram? Speak out your answer. Okay, anti-bump granules. They're to avoid vigorous boiling, to avoid the reaction mixture proceeding up the reflux condenser. Now on the reflux condenser itself, where would the water be coming in and where out? Pause and speak out or add to your diagram where the water comes in and the water comes out of the condenser. Okay, so we have cold water in at the bottom and cold water, it will actually be warmed, but I've called it cold water out at the top. Obviously the temperature of the water increases as it cools the vapors in the condenser. Now, the condenser prevents the escape of volatile reactants and or products. It may well be that the temperature of the reaction mixture is above that of the boiling point of either the reactants or of a particular product. That product or reactant will evaporate, but it will be condensed in the condenser and returned to the reaction mixture. Now, the key examples in your PAG program would be the complete oxidation of ethanol to ethanoic acid, and you may also have done the dehydration of cyclohexanol to form cyclohexene. Moving on to distillation. Pause and complete the diagram for the glassware setup for distillation. Okay, so I'm going to reveal mine. Here we have it. 2 or 3 important things to note. Firstly, the position of the thermometer bulb opposite the outlet. So the evaporate is coming up and its temperature is being measured as it enters the outlet and the condenser. So we can get some identity for that vapor. Notice also that the glassware is an open system. I should have pointed that out on the reflux. It's true for the reflux setup as well. We never have a closed glassware system if you are heating liquids because of the possibility of the buildup of pressure. Water in, water out, as before. And our distillate will of course be impure. At the very best, it would contain some water, it would be wet, but it's more likely to contain some impurities in terms of other reactants or some other products. So you're unlikely to, on first distillation, obtain a pure distillate. It's bound to be impure. Our typical examples from our PAGs are the distillation of carboxylic acids, of ethanoic acid from the reaction mixture after refluxing, but also very important to recall the partial oxidation of ethanol to form ethanal. So as mentioned on the previous slide, you're going to obtain from a distillation an impure liquid distillate. So an important part of your practical program is how to purify an organic liquid. We generally assume that the liquid will form two layers. At that point, you may also, in a method, add something such as sodium hydrogen carbonate to remove some acids. But the separation of the layers in the impure liquid distillate is carried out in a separating funnel. Of course, the lower density liquid will be the upper portion and the more dense would be the lower portion. You'll either be expected to assume that the organic liquid, perhaps in a water organic and distillate mixture, would float on top, be less dense, but more likely you'll be given some density data in the exam question. Having separated or removed the lower layer, you then take the upper layer in this case and you add a solid drying agent such as anhydrous sodium sulfate. This distillate will be wet, still be wet with small amounts of molecules of water mixed in, so you add a chemical drying agent, for example anhydrous sodium sulfate. If you add an excess, you'll see that some solid remains, so you decant the liquid into a flask, leaving the solid anhydrous sodium sulfate behind, and then your final measure is to redistill your now dry distillate and collect at a known target boiling point for your target molecule. So having discussed the purification of an organic liquid, how about an impure organic solid? So this process you will know as recrystallization. So having collected your organic product from your reaction mixture, probably by filtration, you then dissolve that solid in a minimum of hot solvent. So that is a crucial phrase, a minimum of hot solvent. Now, Most textbooks will then include filtration whilst hot, but in most school laboratories that process is generally omitted because of its difficulty. So if we move straight on to the idea of having dissolved your solid in a minimum of hot solvent, you then cool the solution in an ice bath to recrystallize. The crystals that are formed in this process are then filtered at the pump. Might be known as vacuum filtration or filter at the Buchner. Finally, and worth a mark for both ideas, you wash and dry. So generally, in an A-level question, there'll be 3 marks for this process. Dissolve your impure solid in a minimum of hot solvent, and you may be given data to interpret to choose the right solvent. Cool the solution to recrystallize, filter under vacuum, and then wash and dry. Having carried out purification, either of a liquid or of a solid, the question is, now, have I got a pure sample? Well, for an organic liquid, you would measure the boiling point and compare to data. For an organic solid, you would use either a more complex or this very rudimentary melting point apparatus, aluminium block with a space for a thermometer, and then visually you judge the point at which it melts. So you measure the melting point and compare that to data. If you have a sharp melting point or a sharp boiling point that corresponds to the boiling point of the target molecule, then you can say that you have a pure sample. If melting or boiling occurs over a range, then you would say that your sample is still impure and will need further purification, either redistillation in the case of a liquid or repeating the recrystallization process in the case of a solid. Moving on to the calculation of percentage yield. Percentage yield, of course, has a set formula, which you are no doubt familiar with from Year 12 work. The actual moles of product divided by the maximum moles of product times 100. I strongly recommend that you write this expression in terms of numbers of moles, so actual moles divided by maximum moles or maximum theoretical moles of product. It is possible to say actual grams divided by maximum grams, but that often leads to errors. So strong recommendation, percentage yield, the actual numbers of moles of product divided by the maximum theoretical numbers of moles of product times 100. Now, depending on your confidence with a calculator, you may prefer to write the percentage yield in terms of a fraction, that is the numbers of parts in 100. So per 100 is percent. So say percentage yield 65%, so that'll be 65 over 100. And that may help you with your calculation of the correct answer. So let's look at an example. 0.75 grams of hexane 2-one is converted into 2,4-dinitrophenyl hydrazone, which has a molar mass of 282 grams per mole, by reaction with excess 2,4-DMPH. Now, the reaction of a ketone with 2,4-DMPH is on the specification, but the structure 2,4-dinitrophenyl hydrazone is not, but we are given in the question the molar mass. The mass of the purified and dried product was found to be 1.45 grams. So the question is, calculate the percentage yield in this preparation. Pause the lesson, calculate the percentage yield, and then come back to check against my model calculation. Okay, so I'm about to reveal. I initially calculate the moles of hexane 2-one that we're starting with. So that's 0.075 divided by 100. The molar mass of hexane 2-one is 100, so that gives us the numbers of moles of hexane 2-one that we start with. Now, assuming that 1 mole of hexane 2-one makes 1 mole of 2,4-dinitrophenylhydrazone, which is the case, then the maximum theoretical numbers of moles of product is 7.5 times 10 to the minus 3. But the actual moles is based on the mass of product purified and dried. So 1.45 divided by 282, the molar mass which is given to us. So that gives us the numbers of moles of product that were actually formed. Plug those two figures, the maximum moles and the actual moles, into the percentage yield formula, times by 100, comes up with an answer of 68.6%. Let's move to a second example that is more typical of an A-level question paper. Given that the yield of a hexane 2-one conversion to its 2,4-dinitrophenylhydrazone is found to be 68%, calculate the mass of hexane 2-one required to make a 2-gram sample of the hydrazone product. So here you are told the percentage yield and the mass of the desired product. Pause the lesson. See if you can calculate the mass of hexane 2-one required to make 2 grams of the 2,4-dinitrophenylhydrazone product. Come back when you're ready to check against my model answer. Okay, so I'm going to reveal. I'm going to work out what 68% of the maximum moles of 2,4-dinitrophenylhydrazone is numerically. So we've got 2 grams made divided by the molar mass 282. So the 68% of the maximum numbers of moles in the reaction is 7.09. From that, we can then work out the maximum theoretical moles, which is, of course, is 100 divided by 68 times 7.09. So the maximum theoretical moles in this reaction would have been 10.43 times 10 to the minus 3. Now, assuming a 1-to-1 reaction ratio, then the corresponding required moles of hexane 2-one to make 10.43 times 10 to the minus 3 moles of the hydrazone, in theory, would be the same numbers of moles. So the required moles of hexane 2-one is also 10.43 times 10 to the minus 3. So what I've done is I've said that 2 grams is only 68% of the maximum theoretical numbers of moles. So I then work out how many moles 2 grams is and then multiply that up to give me 100%. That 100% would come from a corresponding numbers of moles of hexane 2-one, 10.43 times 10 to the minus 3, assuming a 1-to-1 ratio. And I just convert that into a mass by multiplying by the molar mass of hexane 2-one. So 1.043 grams of hexane 2-one would react to make 2 grams of the hydrazone product, assuming a 68% yield. To finish this lesson, a short introduction to the concept of synthetic routes. So the core idea is that any desired conversion may need to take many stages. That is, starting from a particular molecule and aiming to achieve what's called the target molecule, there is no one-step reaction that is possible. Remember, we are limited to the reactions that are specified in the OCR Chemistry A specification. It may therefore be necessary to convert the starting molecule into an intermediate, and then in a second stage convert the intermediate into a target molecule. It may, in more complex situations, require a four-stage conversion, starting molecule into the intermediate molecule 1, molecule 2, molecule 3, and then into the target molecule. Keep in the front of your mind that you are limited to using the organic reactions that are in the specification. You are not inventing any new reactions. You are simply using what is sometimes referred to as the toolkit, the set of reactions available to you, and putting them into different sequences. Fortunately, there are a limited number of sequences available. Best learned by example, which I strongly suggest you now spend some time working through the next lesson, which will take you through a number of those synthetic routes. For a change on this occasion, I would recommend, before looking in your textbooks, that you move on to the next lesson, synthetic routes, and work your way through that, and then follow my usual advice.